Welcome to this series of lectures on discrete mathematics. My name is David and I am thrilled to be studying this material with you. So let's start right away with this first lecture on logic. Now typically lectures will be split into 2 or more segments. So this video is segment 1 of the first lecture on propositional logic. Before we dive into the specific topics listed here, let me start by explaining why logic in general is not only foundational for discrete math, but also very important to us as computer scientists. I encourage you to always keep in mind some of the reasons why you're required to spend so much time studying this topic. This will help you stay motivated when the material gets tough and when you feel frustrated with this complicated material. Please try not to get lost in the details, and as we move forward, do not lose sight of the big picture and the overall motivation. So why study logic? First, let's consider this question from the perspective of a mathematician. What a mathematician is really interested in is establishing beyond the shadow of a doubt that a specific fact or theorem is true. And as you know in math, there's no room for invalid, ambiguous, or vague reasoning. So the main purpose of logic is to define the basic principles of precise and valid reasoning. In math, theorems are established using airtight proofs. So a training in logic is essential not only to be able to write your own proofs, but also to read and understand proofs written by others, like the author of a textbook, for example. More generally, valid reasoning matters in many other contexts besides math, even in daily life. So when you think about it, logical reasoning is pretty important when you're trying to make a point or win an argument. Now let's focus on computer science applications for a minute. Turns out logic is the foundation of a certain class of software applications called automated reasoning systems. Those include theorem provers, expert systems, and other kinds of artificial intelligence or AI systems. Now there are many other applications of logic in computer science. These include system specification, digital circuit design, software verification, and even programming languages. For example, one of the most used programming languages in AI is called Prolog, and it's entirely based on logic. Now, if all of these applications are not enough to convince you of how useful logic really is, let me bring up a daily life situation that could have been resolved with an extremely basic knowledge of logic. Now, I recommend that you pause the video right now and take a few seconds to read this description and maybe even follow the link at the bottom of the slide. So it turns out that the poor phrasing in this ordinance led to a lawsuit. So imagine how much time and money could have been saved if the authors of this ordinance had studied logic and knew the logical implications of the words and or. Well, I can guarantee you that after you master the material in this lecture, you will not make this kind of mistake. So, now that we understand why logic is so important, let us focus on one particular system of logic called propositional logic. And as the name indicates, the main concept in this system of logic is the proposition. So I will start by defining this concept. But before we go over this particular definition, let me emphasize the importance of definitions in this course. In general, a definition is a precise, unambiguous characterization of the meaning of a word or a phrase, like proposition. So I like to think of a definition as a binding contract. In this metaphor, every time we go over a definition together, you and I are really signing a binding contract, by which we all agree that every single time we use this word later on in the course, we always refer to exactly what its definition states, nothing more, nothing less. Remember that to guarantee that our reasoning and proofs are valid, there cannot be any doubt about what each term really means. So the purpose of a definition is to remove all ambiguity. So please remember that it's really hard to overemphasize the importance of definitions in this course. So let us go over our first definition and thereby sign our first binding contract. As it turns out, you're already familiar with this notion of a proposition. A proposition is just a declarative sentence, that is, a complete sentence that makes a statement and whose meaning is either true or false. By the way, a second way to phrase that second condition is to say that a proposition must have a truth value, either true or false. So let us look at some examples of propositions. This first sentence is a declarative sentence, happens to be true, so it is clearly a valid proposition. Now this second sentence requires a prior definition, that of a prime number. So what is a prime number? It's a positive integer that's greater than 1, that is only divisible by 1 and itself. Since 18 is divisible by 1, 2, 3, 6, 9, and 18, it is not a prime number. However, this sentence is a declarative sentence that happens to be false. Therefore, it is also a proposition. This last sentence, again, is a declarative sentence. It's either true or false. Since it has a truth value, it is a valid proposition. And the fact that it is not known at the present time whether the truth value is true or false does not in any way violate the definition of a proposition. So again, all three sentences here are examples of propositions. Now let's switch gears and consider some counterexamples. Now this sentence is not a proposition because instead of making a statement, it asks a question. Similarly, this sentence is not a proposition because it's an exclamation, not a declarative sentence. This third sentence is called an imperative sentence. Instead of making a statement, it gives an order. So it is not a proposition that's either true or false. Let's continue this introduction to propositions by considering a couple more sentences. Now this sentence is a declarative sentence. It makes a statement. The problem is it does not have a unique or well-defined truth value, so it is not a proposition. I see at least two reasons why the truth value of this sentence is not well-defined. First, whether it is true or false depends on what the weather is like at the time you read the sentence, and that's because of the word today, which is ambiguous. Second, whether a particular weather condition is nice is relative to people's preferences. So for example, I prefer cold and dry days, but some of you may prefer warm and humid days. So in conclusion, since the truth value of this sentence is not determined in a unique way, it is context dependent. In other words, it depends on who is reading the sentence or when the sentence is read. It is not a proposition. This next sentence is another example of a sentence whose truth value is not well defined, even though it is a declarative sentence. And that is because of the variable n, whose value is not specified in the sentence. Since we cannot determine whether the sentence is true without knowing the value of n, which is not part of the sentence, this is not a valid proposition. And notice the similarity between these last two sentences. The ambiguity comes from, in the first case, the word today, which is kind of like a variable whose specific value is not known, and n, which is an explicit variable with an unknown value. In both cases, if the truth value is not well defined, the sentence is not a proposition. I hope that these examples and counterexamples have helped to clarify the concept of a proposition. And since every proposition has a truth value, even though I just used that term a couple times, let's make it official by stating its definition and thereby signing a second binding contract. So in the systems of logic that we're considering in this course, the truth value of a proposition is either true or false. Now, as computer scientists, we are very familiar with bits, so to make it easier on you, I will often use the symbol of the character 1 to mean true and the symbol 0 to mean false. Now remember that the main purpose of logic is to study valid reasoning. So the next step for us will be to study valid reasoning based on propositions. And the particular system of logic that we will study first is called propositional logic, because it is focusing only on propositions. Later on we will study a more powerful system called predicate calculus. But for now, let's stick with propositions. Now notice how the other name for propositional logic is propositional calculus. So in general, a calculus is basically a system that allows you to compute and study some kind of reasoning. Now in our case, we're not going to study functions and integrals and derivatives like you would do in calculus, but instead the calculus we're interested in is how to compute values with propositions. Now, both algebra and calculus use the concept of a variable. But since you are more familiar with that concept in the context of programming languages, I will use an analogy in that area to introduce the next concept. So what is a variable? In programming languages, it's simply a placeholder for a value that either is not known or may even change over time. That's why it's called a variable, because its value may vary. So here is a typical declaration in a high-level language like Java or C. Now the purpose of such a declaration is to first give a name to the variable, in this case x, but also to give a type to the variable. And what that means is, in this particular case, this variable can only be assigned values of type integer. So now we are ready to apply this concept of variables in a context of logic. So a propositional variable is first of all a variable, so it's a placeholder for a value. But the kind of values we're looking at now are propositions, not integers. And since every proposition has a truth value, it's either true or false. A propositional variable can be assigned a truth value. So first, the name of the variables are usually going to be letters from the alphabet starting at P. Whether lowercase or uppercase is fine. And if we ever run out of names, we can just use subscripted letters like P1 and P2. But secondly, besides the name, it should be obvious that the type of these variables is very similar to what you call Boolean variables in programming languages, since the only values they can take on are true or false. So now that we are comfortable with the concepts of proposition, truth value, propositional logic, and propositional variables, it's time that we focus our attention back to the central concept of a proposition to study it in a little bit more detail. So let's start by considering the sentence S1 listed here. Now the first question that should come to mind is whether this is a proposition or not. And the answer is yes, because this is a declarative statement that happens to be true. So what is interesting about this proposition S1 is that it's more complicated than the examples we've seen so far. It's not just that S1 is longer, but when you look at it carefully, you realize that it can be broken down into 3 different and smaller propositions, which are listed here. Let me call these propositions P, Q, and R respectively. Now I want you to convince yourself that for S1 to be true, it must be the case that either R is true or that both P and Q are true. In other words, the the proposition S1 is equivalent to the following expression: R or P and Q. Now in this expression, some of the terms are familiar to you, like the propositions P, Q, and R. On the other hand, there are a couple new terms that we need to explain. The first one are the parentheses. Now these are no different from the parentheses you're used to in algebra or calculus. They are just used to group terms together. So I'm not going to focus on them right now. The second new type of element are the so-called logical connectives or logical operators. A logical operator operates on one or more propositions and yields another proposition. So in our example here, AND is a logical operator that applies to the proposition P and to the proposition Q to yield a new proposition P and Q. Similarly, OR is another logical connective or operator that applies to the proposition R and to the proposition P and Q that we just built, and yields a new proposition, namely this whole expression, which we argued before is equivalent to the proposition S1 up here. So logical operators are no different from arithmetic operators in the sense that, for example, the arithmetic operator plus applies to two numbers and yields another number. Where in this case, logical operators apply to propositions instead of numbers and yield propositions instead of numbers. So when you have such propositions that are built up out of propositions and logical connectives, we call them compound propositions. In other words, they have an internal structure. You can break them down into smaller propositions. And in contrast, the propositions that we had seen before are called atomic propositions because they cannot be decomposed into smaller propositions. So now we have two kinds of propositions, the atomic ones and the compound ones. So when you're given a sentence in English and you're trying to determine whether it's a proposition or not, one step in your reasoning should always be to figure out whether the sentence you're given can be broken down into smaller sentences and more precisely into smaller propositions. And if that's the case, and the whole thing is a proposition, then it's definitely a compound proposition. Otherwise, if it's a proposition that cannot be broken down into smaller propositions, then it's an atomic proposition. Now let's turn our attention to these logical connectives. In this course, we're only going to use 6 of them, and they are shown here in the table. The first 2 are the one we just saw in the previous example. OR is represented with this uppercase V, and is represented by this symbol that looks like an upside down V. The single arrow represents the logical connective called implication or conditional. The double arrow represents the double implication or biconditional. Exclusive OR is slightly different from the regular or inclusive OR and is represented with this symbol here. And finally, the NOT connective is represented with this symbol. So this expression here is read P or Q. This one is read P and Q. The third one is read P implies Q, or if P then Q. This biconditional is read as P if and only if Q. And this one is P exclusive or Q. These 5 operators are binary operators, which means that they apply to 2 operands. Notice how the operator is always placed in between its 2 operands. The only exception here is the unary operator NOT, which only applies to 1 operand. So this expression here is read not P. And notice how the logical connective not is placed in front of its operand. So before we start computing truth values with these logical connectives and these new calculus, we need to make sure we agree on what expressions are correct or well-formed propositions and which expressions are just not acceptable in this calculus. So the rules we need to learn make up the syntax of propositional logic. And so instead of studying those rules formally, let's just illustrate them with some examples. So here is the simplest possible proposition. It's an atomic proposition and it does not contain any logical connective. Another example would be the proposition Q. Now, a slightly more complicated proposition would be to stick a negation or not connective in front of Q to get the not Q proposition. Now remember, not Q means it is not the case that Q is true. So not Q is really the same as Q is false. Now what would happen if we stick another not connective in front of not Q? Well, we would end up with this expression, which, as we just argued, is a well-formed proposition because it starts with a not, which is followed by a valid proposition or a well-formed proposition, namely not Q. So this proposition is syntactically correct or well-formed, and it is read not Q. Now in the next video, when we focus on the interpretation or the meaning of these propositions, we'll see that not Q, in other words, the negation of not Q, can be interpreted as saying it is not the case that not Q. That is, it is not the case that Q is false. In other words, Q is true. So what this will show is that the double negation, not Q, just cancels out and is equivalent to the simplest proposition, Q. But for now, let's just focus on syntax. This third expression is read P and not Q. It is a well-formed proposition since it is the application of the AND logical connector to two operands which are in turn well-formed propositions, namely P on the left side and not Q on the right side. Now, it is often helpful to use parentheses to group terms that go together. So this well-formed proposition is actually equivalent to this proposition, where the elements of the right operand of the AND are grouped together with parentheses. This next expression is read P and Q or R. It contains three propositions and two logical connectives. Now in this case, it's actually not clear whether the Q should be grouped with the AND or with the OR. So I strongly recommend that you use parentheses in this case. And when you do so, the result is that the Q is actually grouped with the AND. So this proposition is equivalent to this one, where you first apply the AND to the P and the Q, and then you apply the OR to the resulting proposition and the R. So at this point, a question must have popped into your mind, namely, why did we group the Q with the AND and not with the OR? And the reason for that is called the order of precedence. In fact, every operator in logic, like in arithmetic, has a precedence. The precedence is a number, and the higher the number, the higher the precedence, meaning the earlier the operator gets to be applied. So it turns out that the AND operator has a higher precedence than the OR operator, which means you get to apply the AND first and then the OR. And so what that means is because the P and the Q are immediately next to the AND, and the AND gets applied first, you must group the P and the Q together like this. And only then do you get to apply the OR. In fact, here is the standard order of precedence for all the operators that we care about, not as the highest level of precedence, which means it gets to be applied right away. At the next lowest level of precedence is and. Then comes the or, the conditional, and then the bidirectional or biconditional. Notice I didn't put the exclusive or, but basically the exclusive or is either at the same level as the or typically it's between the or and and. Now, because of this standard order of precedence, if you had put parentheses around the Q and the or, meaning if you had grouped the Q with the and, you would actually have imposed a different order of precedence. You would have been saying we should apply the or before the and that is perfectly fine, but the only way to achieve this result is to actually use explicit parentheses around the Q and the R to indicate that different interpretation of the sentence. If you don't put parentheses, the standard precedence is applied, and in this case, this expression would be equivalent to that one. So again, the use of parentheses is no different from what you do in algebra. In algebra, if you want to do an addition and a multiplication and you don't indicate by parentheses which one you want to do first, the multiplication always goes first. Why? Because the multiplication has a higher precedence than the addition. If you want to override this precedence, you just use parentheses around the addition to indicate that you really want the addition to be executed first. Now, back to logic. Let us consider the following expression, which is by far the most complicated expression we've seen to this point. So, is this a well-formed proposition? In other words, is it a syntactically valid proposition? To answer this question, we're going to go ahead and fully parenthesize the expression. And in doing so, we're going to illustrate the correct order of precedence, and we will show that there's only one way to interpret this expression, and that it is indeed a valid proposition. So when faced with a large expression like this one, the first thing to do is to locate the logical connectives. So I've written them in red here to make it easier to see. And then you go through the levels of precedence from highest to lowest and start parenthesizing the expression. So I'm going to start with level 5, which you remember is associated with the not connective. So the first step is to go through the expression from left to right and to parenthesize all the negations, like this. Now, I make sure I didn't miss any negations, and I go to the next lower level of precedence, which is level 4, which I'm going to process in green here, and that corresponds to the and logical connective. So again, I go from left to right, find the first and connective, and what I do is I put parentheses immediately around the propositions, around or located next to the and. I find another and here, and notice in this case the leftmost operand of the and is an already parenthesized expression, so I don't have a choice. I must put the parentheses like this. And I'm done with level 4. Now I'm going to proceed to level 3 in blue, which corresponds to the or. Go from left to right. There's actually only one or connective, so I must parenthesize it like this. The left operand and the immediately to the right operand is this one. And we're done with level 3. I will actually continue in blue for level 2, which corresponds to the simple conditional. Again, going from left to right, I find a single such connective, and I must therefore parenthesize the expression like this, with the left operand of the conditional and the right operand of the conditional. Finally, we're down to level 1, which corresponds to the biconditional. And because there's only one biconditional in this expression, it is by definition at the top level of the expression. So instead of putting parentheses around the whole expression, I just stop right here. And this is the final expression with fully parenthesized operators, and I thereby demonstrated that this is indeed a valid or well-formed proposition, which is basically this proposition being equivalent to that one, where this one says if not P is true, then Q and R must be true, whereas this one is saying either P is true or this thing is true. And this thing is saying not R is true and Q is true. Now that we've established that this formula is a well-formed expression in propositional logic, let's consider some counterexamples. That is, let us take a look at some expressions that are not valid propositions because they do not respect the syntactic rules of propositional logic. This first formula is not a proposition because the only way to combine two propositions into a compound proposition is to join them with a logical connective. And here the logical connective is missing. The problem in this second example is that the logical connective is placed after the two operands, whereas the only way to place the logical connective is in between its operands. And so for the same reason, this third example is not a well-formed formula either. In this case, the unary operator not is placed after its operand, and that is against the syntactic rules. Remember that the not must appear right before its operand. In this fifth expression, the not operator precedes another operator, and that is not allowed. Remember that the not logical connective can only precede an atomic proposition or another copy of itself, like in double negation. In this case, the problem is that an AND logical connector is directly followed by an OR, and that is not allowed, since an OR, or an AND for that matter, should always be in between its two operands. This last expression contains four distinct atomic propositions, P1 through P4. Notice that there are two occurrences of the same proposition P1 in this formula, and that is not a problem at all. The problem in this case is with the parentheses. Notice how the parentheses before P3 is closed after P4. So that's just fine. However, the parentheses before P2 is never closed. So what this means is this expression is missing one parenthesis. And that's enough to break the rule of syntax. So in other words, this is not a proposition or a well-formed formula in propositional logic. So this concludes our first segment, where we defined important concepts like proposition, propositional logic, truth value, logical connectives, and compound propositions. And then we focused exclusively on the syntax of propositional logic. In the second segment of this lecture, we will turn our attention to the semantics instead of the syntax.